The subject of this lecture is Introduction to Structure and Properties of Proteins. However, we will start this lecture by observing substances called amino acids. The name amino acids does not reveal the connection these substances have to proteins. In fact, however, amino acids have everything to do with proteins because they are the building blocks of proteins. Therefore, studying the properties of amino acids constitutes the basis of understanding proteins. Amino acids are quite unusual organic substances, as can be seen from their general structural formula. Here we see a group possessing acidic properties, carboxyl group, and a group possessing basic properties, amino group, attached to the same carbon atom. In other words, the structure of the amino acid, as it is drawn here, requires the coexistence of a weak acid, carboxylic acid, with a weak base, an amine. This is impossible. Thus, the weak acid will immediately react with the weak base by transferring the proton from the carboxyl group to the amino group. This leads to the formation of a quite unusual ion, an ion that has both a positive and a negative charge. These kinds of ions are called Zwitter ions, or internal salts. Interestingly enough, amino acids exist as Zwitter ions not only in water solutions, but also in solid state. Amino acids do not exist as Zwitter ions at all pH values. The pH value at which an amino acid exists as a Zwitter ion is called isoelectric point. In this instance, if this group R is neutral, the isoelectric point of this amino acid will be somewhere around 6. Now let us see what will happen if we decrease the pH of the solution in which this amino acid is the solute. Decrease of pH is the increase of the concentration of hydrogen cations, the increase of the proton concentration. The concentration of the protons can be increased by the addition of a source of protons, such as a strong acid, an acid of the type of hydrochloric acid. Let us introduce 1 mole of protons, say by the addition of hydrochloric acid solution, to the solution containing this 1 mole of amino acid. If we don't know the properties of these entities, it may appear to us that after the addition of hydrochloric acid to the solution, there will be 2 separate entities existing independently of each other, namely the anion of the carboxylic acid and the hydrogen cation, the proton. This is incorrect. It is not possible for the anion of a weak acid such as carboxylic acid to coexist with a proton in solution as separate entities. The anion of a weak acid is in fact the conjugate base of this weak acid. Recall that the conjugate base of a weak acid is a strong base. That is, it is a strong acceptor of protons. In other words, as soon as these protons appear in the solution, they are immediately accepted by this strong base, and the carboxyl group of the carboxylic acid is restored. This carboxylic acid holds on to its proton very strongly. After all, this is what all weak acids do. They hold on to their protons very strongly and do not give them off readily. Now notice that despite the fact that by lowering pH the acidic part of the molecule is neutralized, there is still a charge remaining on the molecule of the amino acid. Now let's go back to to the amino acid zwitter ion, which, as it was mentioned, exists at the isoelectric point. That is, at pH value where there is both positive and negative charge on the molecule of the amino acid. Let us see what will happen if we start increasing the pH above the isoelectric point. Increase of pH occurs when the concentration of hydroxide ions is increased. Concentration of hydroxide ions can be increased by the addition of a source of hydroxide ions, such as, for instance, sodium hydroxide solution. Let us add 1 mole of hydroxide ions to the solution containing this 1 mole of amino acid. Also, let us observe that the ammonium ion in the amino acid has the potential to release 1 proton. After the addition of the hydroxide ion to the solution, a competition between 2 bases for the acquisition of this proton starts to take place. These 2 bases are, on the one hand, the hydroxide ion itself, and on the other, the amino group that will remain if this proton were released. The winner of this competition is the hydroxide ion, which acquires the proton and forms water with it. Now this water joins the rest of the molecules of water in which this amino acid is dissolved in. The hydroxide ion prevails in the competition with the amine for the proton because by its very nature the hydroxide ion is a stronger base than the amine. In other words, the tendency of the hydroxide ion to accept a proton is stronger than that of the amine. Now we see that at pH above the isoelectric point, the amino acid ion has only a negative charge. Recall that at pH below the isoelectric point, amino acid also has only 1 type of charge, positive. Amino acids exist as ions at all pH values. Amino acids are ions, zwitter ions, even when solid. Therefore, the physical properties of amino acids are typical for ionic solids. They have high melting points, they are readily soluble in water, and so on. In conclusion, realize that the addition of protons or hydroxide ions, which we achieve through the addition of hydrochloric acid or sodium hydroxide, constitutes change of pH. Amino acid resists this change of pH. Lowering of pH is resisted by neutralizing of incoming protons and binding them into a carboxyl group. Increase of pH is resisted by neutralizing of the hydroxide ions and turning them into water by the donation of a proton from the ammonium group. Solutions that resist change of pH are called buffer solutions. Therefore, solutions of amino acids are buffer solutions. So far, we spoke about amino acids in general, without regard to their existence in biological systems. After all, amino acids can be synthesized in the laboratory and can be looked upon as another peculiar chemical substance. To make the leap from this general observation to the narrower group of amino acids pertinent to biological systems, in particular to proteins, we have to observe another interesting and important property of amino acids, namely the fact that in their molecule there is at least 1 carbon atom that has 4 different groups attached to it. This is the so-called chiral carbon atom. A molecule containing 1 or more chiral carbon atoms is said to be a chiral molecule. As a matter of detail, it may be noted that there are chiral molecules that don't have a chiral carbon atom. And also that there are molecules that have 2 or more chiral carbon atoms that are not chiral. Such molecules are rare and are not important for the present discussion. A chiral molecule cannot be superimposed on its mirror image. We can even turn it around. Molecules that are non-superimposable mirror images of each other are called enantiomers. We can see that this is a very subtle type of stereoisomerism. Even the shapes of the molecules are the same. The only structural difference between the two molecules is the direction of arrangement of atoms in the molecules. Because the structure of the enantiomer pair molecules is similar, the properties of these two molecules are the same, except for two. First, the rate of the reaction of one of the enantiomers with a molecule that is chiral is higher than the rate of the reaction of the other enantiomer with the same chiral molecule. And second, the two enantiomers rotate the plane of polarized light in opposite directions. Polarization and rotation of the plane of the polarized light is discussed elsewhere. One of the enantiomers that rotates the plane of the polarized light many times to the left is denoted by the letter L. The other enantiomer that rotates the plane of the polarized light in the opposite direction, many times to the right, is denoted by the letter D. What is important to be emphasized is that is the L form of the enantiomer that is the predominant form of the amino acids in nature. The D form of the enantiomer exists very rarely. Interestingly, in our discussions so far of the properties of amino acids in general, we use the D form of the enantiomer. As mentioned, however, in biological systems, it is the L form of the enantiomer that is the predominant form. There are only 20 different amino acids that exist in biological systems. These concrete 20 amino acids are shown in a separate presentation. Some of these amino acids are called essential because they are not synthesized in the organism. Nevertheless, they are needed and have to be supplied by the diet. An amino acid can react with another amino acid to form the so-called peptide linkage. As you can see, the peptide linkage is in its essence an amide because we have a carbonyl group connected to a nitrogen atom. When two amino acids are connected by a peptide linkage, the product is called dipeptide. There may be many amino acids connected by peptide linkages, and then we have a polypeptide. A protein is a polypeptide containing more than 50 amino acids connected by peptide linkages in a chain. The individual amino acids that are part of the polypeptide chain are referred to as the residues. Also, by convention, we write the polypeptide chain with the free amino group on the left-hand side, and we refer to it as the N-terminal, while the free carboxyl group is written on the right-hand side and we refer to it as the C terminal. The peptide linkages and the carbon atoms that are connected by the peptide linkages in the polypeptide chain constitute the so-called backbone of the polypeptide. The R groups are called the side chains of the polypeptide. Proteins themselves can exist as Zwitter ions or can be buffers, not only because of the amino and carboxyl groups, as in the case of amino acids, as discussed so far, but also because of acidic and basic properties of portions of the side chains in the molecule of the protein. Sometimes, as shown here, acidic groups in a protein molecule may outnumber the basic groups. In such a case, the isoelectric point of such a protein will be in the acidic region. Indeed, the extra acidic groups have to be neutralized by the decrease of pH or by the addition of protons, so that their number matches the number of the basic groups. Based on the discussion so far, it should not be difficult to figure out at what pH the isoelectric point is going to be of a protein that has equal number of basic and acidic groups. Also, it should not be difficult to figure out at what pH the isoelectric point of a protein whose basic groups outnumber the acidic groups will be. Because of the importance of hydrogen bonding for the present discussion, we'll digress shortly and we'll recall that in order for a hydrogen bond to be formed between two molecules, two conditions have to be fulfilled. The first condition is that both molecules have to have oxygen, nitrogen, or fluorine atom as part of their structure. And the second condition is that at least one of the molecules has to have hydrogen directly connected to oxygen, nitrogen, or fluorine. Here is an example of two molecules. These are two molecules of dimethyl ether, both of which have oxygen atoms as part of their structure. Obviously, both of them have hydrogens. However, none of these hydrogens is directly connected to the oxygen atom. Therefore, the second condition for the formation of hydrogen bond is not fulfilled here, and no hydrogen bond is formed between these two molecules. The sequence of the individual amino acids, the residues in the chain of the polypeptide or the protein, determines the so-called primary structure of the polypeptides or proteins. Proteins, however, are characterized also by secondary, tertiary, and even quaternary structure. This is very important for their functioning in biological systems. The secondary structure of the protein is determined by the oxygen and some of the hydrogen atoms in the backbone of the protein molecule. These oxygen and hydrogen atoms in the backbone of the protein molecule form hydrogen bonds. The side chains can be neutral, but also polar, acidic, or basic. Therefore, there can be interactions between these side chains. Interactions between the side chains in the protein molecule determine the tertiary structure of the protein. Some proteins that have more than one chain may also have a quaternary structure. Obviously, proteins always have primary structure. When proteins have secondary structure, it can be alpha helix or beta-pleated sheet. In alpha helix, the backbone of the protein molecule forms a spiral due to the hydrogen bonds that were already mentioned between the oxygen and some of the hydrogen atoms from the backbone of the protein molecule. In beta-pleated sheet, parts of the protein molecule align themselves parallel to each other, and again hydrogen bonds are formed between the oxygen and some of the hydrogen atoms from the backbone of the protein molecule. The rest of the molecule exists as random coil. Tertiary structure of the proteins evolves from the properties of the R groups in the various amino acids that make up the protein. As mentioned, these R groups form the so-called side chains in the protein molecule. Here, by this curve, we have drawn symbolically the backbone of the protein molecule. Explicitly are shown only some of the functional groups in the side chains of the protein molecule. As mentioned, the side chains can be nonpolar, acidic, basic, polar, and so on. Ion-ion interactions may take place between side chains that have portions that are ionized acids and bases, and this may be the cause for the tertiary structure at this part of the protein molecule. At another part of the protein molecule, there may be hydrogen bonding taking place between portions of the side chains that are polar. Non-polar portions of the side chains may push out solvent water molecules and attract each other through the so-called hydrophobic interactions. Also, disulfide bridges may be formed in some parts of the protein molecule, thus determining the tertiary structure. As it was mentioned, not only the primary structure, but also maintaining the secondary, tertiary, and in some instances quaternary structure is very important for the functioning of the protein in biological systems. Destruction of the secondary, tertiary, and in some instances quaternary structure is called denaturation of the protein. Physical and chemical factors may be the cause for the denaturation of a protein. For instance, acids, bases, and salts can interfere with the ion-ion interactions. Heat may destroy the hydrogen bonding. Surface active agents may interfere with the hydrophobic interactions. Some reducing agents may destroy the disulfide bridges. This brings us to the end of our lecture, in which the emphasis was placed on the chemical side of amino acids and proteins. Many facts of biological nature were left unmentioned. Such facts and topics are covered in courses more closely related to biology. It is hoped that understanding the chemistry of amino acids and proteins will facilitate comprehension of their biological aspect.